We are now going to look at the first real aspect of computer design, that is the instruction set design. As we will see, the instruction set can be a critical component of the design of a computer and can go a long way in determining the performance of a particular computer. Let's begin by understanding what an instruction set is and why we need an instruction set. Let us look at a couple of code examples using higher level language. The first line here shown is using C or C++ language, and it involves a statement which has at least 3 function calls. Depending on the runtime behavior, there could be 4 function calls, and we know what this statement does. It assigns a particular value to this pointer f arrow next. The second line here is in a scripting language called Perl, and here we have a string $line, and this statement substitutes the string ABC with XYZ wherever ABC occurs in the string $line. High-level languages provide this kind of rich constructs so that it is simple for programmers to express what they want. However, as it is obvious to see, this is too complex to be implemented directly in the hardware machine. So the solution is to express the complex statement as a sequence of simple statements. This is where the instruction set comes in. Instruction set is nothing but the set of relatively simple instructions using which higher level language statements such as the example shown above can be expressed and executed in hardware. It would be a good exercise for you to think of some examples of higher level language statement, a single higher level language statement, any language that you're familiar with, which you think is too complicated to be implemented directly in hardware. Let us use this example which we have come across earlier. Here we have a simple piece of C code which is translated into assembly code. Instruction set design thus deals with what is the set of instructions in assembly language code which we need to support so that all higher level language statements can be expressed using a combination of these instructions in the assembly language. We can now revisit this language hierarchy which we have seen earlier. We saw that algorithm and higher level language are machine or hardware independent, and whatever is below here, assembly language, machine language and digital logic, are machine or hardware specific. So we can think of these 3 layers below to represent the machine or the hardware, and these 2 layers above to represent the software. In this perspective, the instruction set is nothing but the interface between the software and the hardware. In other words, the interface between the machine independent and the machine specific part. The instruction set defines the machine, and this interface design is thus very important. In computer systems in general, interface design is a central part. Interface is critical to define before the implementation. Interface allows abstraction or independence across the different layers, and this is the reason why you can run different pieces of software on the same machine. One challenge in interface design is of course that the interface should be easy to use by the layer above while also allowing a efficient implementation by the layers below. As I have said, the instruction set defines the machine or hardware. If you translate a piece of higher level language code using MIPS instruction set into MIPS assembly code, then it is suitable for running on MIPS hardware. Likewise, if you use x86 instruction set to translate the higher level language code, then it is suitable for running on x86 machine. Likewise, if you use ARM's instruction set, it is suitable for running on ARM hardware. Recall the notion of a stored program in the von Neumann architecture, where the instructions representing the program reside in memory, and the memory also has the data on which the instructions operate. In this context, the processor essentially does 2 things in a loop. It fetches an instruction from memory and it executes the instruction, and then it goes back in a loop to fetch the next instruction. The execution of an instruction itself may involve data transfer from or to memory. We now have the context in which to discuss various kinds of instructions. In abstract, we have 2 parts to an instruction, the operation and the operand. Let's take an example. Here we have the variable a being assigned a value which is the sum of addition of variables b and c. Can you here identify what the operation is and what the operands are? The operation involved here is the addition operation, and the operands are B, C and also A. Although in mathematical terms we do not typically consider the result to be an operand, in computer architecture terms we are going to consider the result also as an operand. This is because the result of addition of B and C gets stored into a location called A. So in that sense, for this whole operation, A is also an operand. Given that an instruction has two aspects, operation and operand, the question of what should be the instruction set of a machine essentially translates to what set of operations should we support and what set of operands for each of these operations. We will learn about these in the context of the MIPS instruction set. We'll use the MIPS instruction set as an example, not only because it is simple and thus easy for learning, but also a simple instruction set, it turns out, can oftentimes give better performance than complicated instruction sets. An example of a complicated instruction set would be the x86 instruction set. It is now time to introduce the notion of registers. Registers are very fast operands. Registers are very small memory which reside inside the processor. They are an integral part of a processor. The fact that registers are small, this memory is small, implies that it is very fast to read and write. This is important in determining the performance of the processor. The small size of the memory representing registers also means that it is easy to encode instructions from assembly language to machine language, as we will see when we come to instruction encoding. In one perspective, registers can be considered as part of the memory hierarchy. However, they are an integral part of the instruction set architecture. That is, they are an integral part of the hardware to software interface. The particular MIPS machine which we are going to use as example has 32 registers, each of 32 bits. Some terminology: 32 bits or 4 bytes is often called one word, and half of that, 16 bits, is called a half word. One word is the common case of unit of data in MIPS, although there are instructions which support other units of data. In this course, we are going to be concerned about 32-bit architecture, also called MIPS 32. There is also a 64-bit version of the MIPS architecture called MIPS 64. Today, both 32-bit and 64-bit machines are very common, although many low-end embedded platforms could be using 8-bit or 16-bit architectures as well. So this is our first assembly language instruction in MIPS, the add instruction. It has exactly 3 operands, 2 of which are added and stored onto the third. The format is as given. The result is specified first, followed by the 2 operands which are added together. As an example, add $S3, $S1, $S2. This instruction will add the contents of S1 and S2 and store it onto S3. $S1, $S2 and $S3 are registers in the MIPS machine. It turns out that the add instruction supported by MIPS has exactly 3 operands only. Natural question is, why not support more operands? After all, you can add more than 2 numbers together. Why not support a variable number of operands? Think about that question. The answer lies in the design principle that regularity implies simplicity and simplicity usually implies fast implementation. We will see this more explicitly when we discuss the implementation of the MIPS instruction set in hardware. As I said, all 3 operands of the add instruction are registers. There are actually 32 registers which are numbered 0 to 31. In assembly language, these registers are called $0 to $31. It's not that $0 corresponds to $S0. In fact, $S0 corresponds to $16 and $S7 corresponds to $23. $S0, $S1 and so on are in some sense symbolic names for the numbered registers $0 to $31. Now there's a variant of the add instruction. It's actually a separate instruction called add I, which stands for add immediate. Here, one of the operands is a constant or an immediate operand. It is called an immediate operand because the operand appears as part of the instruction itself. A question for you to think about in this context is, why should there be a separate instruction add I when there is already the add instruction? The answer lies in the fact that many higher level language constructs use immediate operands frequently. And here the design principle of making the common case fast kicks in. So if there is heavy use of immediate operands in higher level language, it is useful to have a specific instruction which supports such immediate operands. So most MIPS instructions have a version with immediate operands, which is also supported as part of the MIPS instruction set. Now think about various higher level language programs you have written and think of a common case use of constant addition, that is, addition of a constant to a variable. The next set of important instructions in the MIPS instruction set correspond to memory operations. These are called load and store. The terminology is with respect to the CPU. That is, the instruction load word loads one word of data from memory onto one of the registers within the CPU, and store stores one word of data from one of the registers in the CPU to memory. Note that the unit of data transfer here is one word, which is the same as the width of the registers in MIPS. These instructions are also called data transfer instructions because they transfer data between memory and the registers. Now when you talk about main memory, we have a main memory which is occupying a 32-bit address space. That is, an address in this memory needs 32 bits to specify a particular location. In this diagram here on the left hand side, we have various memory addresses shown in hexadecimal. Each of this is 32 bits in width. You can also see that this goes in multiples of 4. This is because I have shown here memory arranged as one word units. Now in the load word instruction as well as the store word instruction, there needs to be a memory address specified. This memory address 32-bit value is specified as the addition of the value in a base register plus an offset which is specified as part of an instruction. The format of load word is given here. We specify the destination register first, followed by the offset and within parentheses the base register. An example is shown here, load word $S1 for $S0. What this means is that to derive the memory address, I am going to add 4 with the value in register S0, and that will give me a 32-bit address, and that's the memory location from which I will fetch one word of data and store it onto register S1. The reverse happens in the case of store word. The address specification is similar to the case of load word. MIPS follows this convention where the first thing specified after the instruction specification, the first operand is always the destination. So in store word, the memory specification comes as the destination and the source register is specified after that. One question for you in this context is, why is this base register plus offset specification useful? After all, the same functionality can also be achieved by using just one register, the base register. So why is this functionality useful? You have to think in terms of what higher level language functionality can be easily supported by this feature of having base register plus offset specification of the address in the load word and store word instructions. The load word and store word instruction have an alignment restriction. This means that the address which is specified has to be a multiple of 4. As to why this is the case, we will answer later. We will also answer later as to what will happen if you try to run a program in which the specified address is not a multiple of 4. Let's take a pause and test your understanding of the MIPS instruction set design by a few questions. First is a sub-I or subtract immediate instruction needed? Subtracting a constant from a register. Is such an instruction needed? Why or why not? Next question is a sub instruction needed? Subtracting instruction. We have the add instruction. Is a separate sub instruction needed? Why or why not? Now let's put our understanding to some real test by translating a C statement into MIPS assembly language. So this statement here says A of 300 equals X plus A of 200. Assume that A is an array of 32-bit integers and X is also a 32-bit integer. As you start thinking about how to translate this into MIPS assembly language, you will run into some problems. You will need more information than what I have given here. Think about what more information you need. You will need information about what is A, what is X. So these are C language variables, but we so far know to write MIPS instructions only in terms of MIPS registers. So assume that A corresponds to MIPS register $S0 and X corresponds to MIPS register $S1. Now you should be able to translate that statement into MIPS assembly language code. So here is the answer. You first have to load A of 200 onto a register. Here I have used another register called T0, $T0. One subtlety here is that the offset which you add with the base address of the array, which is A, which is essentially $S0, the base address you have to add 800. This is because this is an array of 32-bit integers. That means that the address is 800 bytes. The address of A200 is 800 bytes away from the address of A. Now I have used another register $T1 to store the addition of $T0 and $S1, which is essentially the addition of X and A200, and then I use this store word instruction to store it onto A300. Note again that I am using an offset here of 1200, which is 4 times 300. Now you may have used different registers different from $T0 or $T1 in your solution. Usually registers $T0 to $T9 are used for temporary values in MIPS assembly language. So here is another set of 10 registers in the MIPS set of 32 registers we have learned so far. Continuing along the same lines, now translate this statement A300 equals X plus A of I plus J, assuming again that all of these are 32-bit integers. A is an array of 32-bit integers, X is a 32-bit integer, and so are I and J. Can you use it using the instructions known to you so far? Let's give it a try. You can assume that I corresponds to register $S2 and J corresponds to register $S3. So here is the solution. So in this solution, first I add I and J, and then I have to multiply it by 4, remember? You could do this multiplication by 4 in a few ways. Here in this solution, I have used the mul I instruction, which I have not introduced so far, but here I am introducing it. This multiplies a register with a given immediate operand. Given it is multiplication by 4, you could also have achieved it by having 2 add instructions, each add instruction doubling the value from earlier by adding a value to itself. There is also an easier way to do it, which we will look at shortly. But for now, let's continue with this example. So after having multiplied I plus J by 4, I need to add that value to A to get the offset. Note that in the load word instruction, the offset has to be a constant. So I need to get the address directly in this particular register. Here I have used $T3. So this load word now gets in $T0 the value of I plus J, and then the rest of it is similar to the previous example. Now in both these exercise examples we have seen there is a notion of register assignment. That is, variables in higher level language are statically assigned to specific registers in different portions of the code. This assignment is typically done by the compiler at the time of compilation. And this is one of the important jobs of the compiler. The compiler has to track as to which section of the code, which register is mapped to which variable of the higher level language code. Let's now look at a few more instructions. These are the set of logical operations, bitwise logical operations, which are possible in MIPS. First, we have the shift left logical SLL, which is corresponding to the C or C++ or Java left shift operations. There is a corresponding SRL for shift right logical. There is a bitwise AND, both register operation as well as register immediate operation. Similarly, there is a bitwise OR, register operation being OR and register immediate operation being ORI. There is a bit by bit NOR operation also, using which you can achieve bit by bit NOT. So think of how you can achieve bit by bit NOT or bit by bit toggling using the NOR operation. Now before we can look at the next set of instructions in the MIPS instruction set, we need to introduce the notion of the program counter. Recall the notion of a stored program, where the program or the instructions are themselves stored in memory and the CPU essentially fetches instruction one by one and executes the fetch instruction. So here we have a notion of a program counter, which is nothing but a special 32-bit register which has the address of the current instruction. That is, it points to the current instruction. This is the address using which the processor fetches instructions from memory. Now, during normal sequential execution, can you tell by what value PC will be changed between one instruction and the next? Since instructions are also 32-bit in the MIPS 32-bit architecture, for sequential execution, the PC value will be incremented by 4 for each instruction, corresponding to 4 bytes or 1 word. Now, not all steps in execution are sequential. You know that in higher level language, we can have non-sequential execution. Now, this has to be implemented by special manipulation of the program counter. In the MIPS instruction set, it turns out that the PC, which is also a 32-bit register, is not really part of the register file. That is, it does not correspond to any of the registers $0 to $31, which we have talked about earlier. In MIPS, only special instructions can be used for manipulation of the value of the PC. In some other architectures, the program counter is also part of the regular register file, and we can have arithmetic or data transfer instructions involving the PC. However, in MIPS, the PC register is not part of the register file, which means that you cannot, for example, use add or load word instructions directly with the PC as one of the operands. We are now ready to look at a set of instructions called branch instructions. These are used to support non-sequential execution in higher level language code. Now think of the various instances of non-sequential execution in higher level language code. So here is a list of common instances of non-sequential execution: if then else conditional execution, possibly nested, loops, procedures and function calls, goto supported by certain programming languages, and switch statements, which is a special case of nested if then else. So we are now going to see how MIPS instruction set is going to support these higher level language programming constructs. The simplest of branch instructions are these 3 instructions, 2 of which are conditional branches and 1 unconditional branch. The 2 conditional branch instructions are BEQ and BNE, which stand for branch if equal and branch if not equal. In the BEQ instruction, 2 register operands are given, their values are compared, and if the values are equal, the branch is taken. And in the BNE instruction, the branch is taken if the values are not equal. If the branch condition is not satisfied, for example in BEQ, if the register values are unequal, then sequential execution continues. That is why BEQ and BNE are called conditional branch instruction. As opposed to these, the J instruction, which stands for jump, is an unconditional branch. The branch is always taken. Now when we say the branch is taken, it means that execution moves to the branch target. And how is the branch target specified? Note that each of these instructions has a specification of the branch target. In assembly language, the target specification is in terms of a label. A label is nothing but a human readable string, a name given to a particular line of assembly language code. Such a label is similar to the goto labels which are specified in some higher level languages. So how is this human readable label converted to machine language in zeros and ones? During this conversion from assembly language to machine language of the label gets specified as a PC relative offset. We will look at this in more detail when we learn about instruction encoding. It is one of the jobs of the assembler to compute the PC relative offset from the label. This is part of the translation of the assembly language to the machine language. Let us now see if you can put to use what you have learned so far. Convert this if then else statement in C language to MIPS assembly language. As earlier, we can assume that each of these variables is a 32-bit integer, and as has been the convention in the example so far, we can assume that the first variable in the higher level language statement corresponds to $S0. Here x corresponds to $S0 and the second variable corresponds to $S1. So y corresponds to $S1 and so on. So now translate this code into MIPS assembly language. So here is my solution. I have 2 labels specified. One is the beginning of the else part of the code and the other is named exit for the end of the code. So to implement the if condition, I use a branch if not equal. So what I do is compare $S0 or X with $0. So what is this $0? MIPS has this register $0 which is written as $0 as shown here. It also corresponds to register number 0. So you can also write it as $0 here. This register is always fixed to the value 0. So I am using this to compare X with 0. And if the values are not equal, then I go to the else part. If the values are indeed equal, the branch is not taken. So this hits the if part. This is the if part of the code. Once the if part of the code is over, I need to jump past the else part. That is why I have an unconditional branch here in terms of a jump instruction. And then there is the else part of the code. Here is a thought exercise for you. Why is there a special register which is always fixed to the value 0? The answer lies in the design principle of making the common case fast. It turns out that the use of comparison with 0 is so common, is very common in higher level language statements, that there is special support for that in MIPS assembly language. And that is why we have a special register which is always fixed to the value 0. Here is another exercise for you to test your understanding. Convert this while loop C code to MIPS assembly language. You can make assumptions as usual. Here is my solution. I begin the loop with a label begin, and then the first assembly language statement is a shift left logical. What do you think this does? Yeah, this multiplies the value of I by 4. Shifting by 2 bits to the left is equivalent to multiplying the integer value by 4. Then the multiplied value is added to A to get the address of A of I, and then that particular memory word is loaded onto register T1, that is the load word instruction. Following that is the branch if equal. If the value AI happens to be 0, I have to exit the loop. Otherwise, I have to execute the body of the loop, which is the add I instruction. Here I have an unconditional jump to the beginning of the loop. A question for you is, in this above solution, is $T1 really needed? Can you do away with the use of this additional temporary register $T1? We have so far looked at branch instructions which support testing of equality. Branch if equal as well as branch if not equal test for equality. However, there are several situations where we want to compare something not on equality but on value lesser than or greater than. It turns out for this we need help from other instructions. So there is this set less than or SLT instruction, which sets the destination register to 1 if the first operand value is lesser than the second operand value. Otherwise, it sets the destination register to 0. There is also SLTI, which uses an immediate operand as opposed to a second register operand. Now, if we want to do a comparison of lesser than, you can follow up an SLT instruction with a BNE or BEQ instruction, as the case may be. A thinking exercise at this juncture is, do we need separate instructions for comparison of lesser than or equal to, greater than or equal to comparisons? What do you think? So note that in this scheme of things, if you want to compare one register value to another register value lesser than and then branch based upon that condition, it's a two-step process. First, you have to use the SLT instruction followed by a BNE or BEQ instruction. So natural question which arises is, why doesn't MIPS support a single BLT or BLTI instruction? That is branch if less than. Is there such an instruction supported? It turns out it's not. Why? Can you think? We will be able to appreciate the answer to this question of why BLT is not supported later on when we learn about the implementation of MIPS in hardware. But the high level reason is that supporting BLT instruction would likely slow down all instructions because the underlying hardware implementation of the machine of the instruction set would be slower. So now that we know how to compare less than greater than values to implement branch conditions, take up this exercise of converting this piece of C code to MIPS assembly language. Make the usual assumptions. So here is my solution. Note how I have used this add I instruction with the $0 register to initialize I to 0. And then the loop begins by checking whether I is less than 10. For this I have used the SLTI instruction. So this register T0 is set if I is less than 10. That means it is not set, it is 0 if it is greater than or equal to 10, in which case I exit the loop. I come over here, and these instructions correspond to the body of the for loop. Note that the body of the for loop ends with addition of 1 to I. A question for you to think about is, can you use lesser number of temporary registers than what I have used here in my solution?